Hi everyone. In this video, we will talk about one-sided limits. Let's start with an exercise. What is the limit of this function at x equal to 3? If you would like to try this exercise on your own first, you can download these notes using the link in the video description. To determine the limit at x equal to 3, first I find x equal to 3 on the x-axis. Then I use inputs that approach 3 from the left. When I do so, the outputs of my function get closer and closer to 2. So the limit of this function, as x approaches 3 from the left, is 2. Then I use inputs that approach 3 from the right. When I do so, the outputs of this function get closer and closer to 1. So the limit of this function, as x approaches 3 from the right, is 1. Because a limit of a function at a particular point can be just one number, and we got a different value from the left and from the right, we say that the limit of this function, as x approaches 3, does not exist. It was a lot to write. The limit of f of x as x approaches 3 from the left is 2. Mathematicians have a shorter way of writing this. They would write instead the limit of f of x as x approaches 3, and to say from the left, they would add a minus sign in the exponent of 3. And we know that this left-hand limit is 2. To say the limit from the right, they would say the limit of the function f of x as x approaches 3, and to say from the right, they would add a plus sign in the exponent of 3. And we know that this right-hand limit is 1. Because these two numbers were not the same, we concluded that the general limit did not exist. This is a theorem mathematicians proved. This theorem says that a limit of a function exists and equals some number L, and that happens if and only if the left-hand limit and the right-hand limit also exist and equal to L. That is exactly what we did in the above exercise. The left-hand limit was different than the right-hand limit, so we concluded that the general limit did not exist. If the left-hand limit was the same as the right-hand limit, we would be able to conclude that the general limit exists. This theorem uses lots of words. You can write this theorem using symbols. You could say that the limit of a function as x approaches any number, let's say as x approaches a, exists and equals to a number L. That happens if and only if, I'm using a shorthand for if and only if, IFF, the limit of the function as x approaches a from the left is also L, and the limit of this function as x approaches a from the right is also L. The meaning of if and only if is the following. This is a sentence that works both ways. It works this way and it works this way. For example, if a limit of some function at some number a is, let's say, 5, then the left-hand limit at that number is also 5, and the right-hand limit at that number is also 5. On the other hand, if the limit of some function as x approaches some number a from the left is, let's say, 7, and the right-hand limit is also 7, then you can conclude that the general limit at that number also equals 7. Let's see if we can apply the above theorem to a problem. If you would like to try this problem on your own first, this would be a good time to stop the video. Estimate the provided limits of the function f of x below. First, we must find the limit as x approaches -2 from the left. I find -2 on the x-axis, I approach it from the left using the inputs, and I see that the outputs of my function get closer and closer to -1. So the limit, the left-hand limit, is -1. Now I must find the right-hand limit at -2. I approach -2 from the right. and I see that the outputs of my function get closer and closer to -1. The left-hand limit is -1. The right-hand limit is -1. This means I can conclude that the general limit at -2 exists and also equals -1 by the theorem we just discussed. Let's see if we can do something similar at x equal to 1. First, I must find the limit as x approaches 1 from the left. I find x equal to 1 on the x-axis. I approach it from the left, and I see that the values of my function get closer and closer to the value of 2. So the left-hand limit is 2. As I approach x equal to 1, using inputs on the right side of 1, the outputs of my function get closer and closer to the value of 3. Because the left-hand limit is different than the right-hand limit, I can conclude, without even looking at the graph of my function, that the limit as x approaches 1 does not exist. I have one more problem for us to try. If you would like to try this problem on your own first, again, this is a good time to stop the video. This time, we must draw a graph that satisfies all these conditions. Let's draw a graph by taking a look at the conditions one by one. First, the value of the function at -2 must be 4. I find x equal to -2. I know that the value of the function must be 4. So I add a solid dot with coordinates -2 and 4. Then, the limit of this function, as x approaches -2, from the left must be 4. So as I'm approaching -2 from the left, I must be getting closer and closer to 4. The easiest way to achieve that is to draw a piece of the graph that gets closer and closer to that dot from the left. Then, I know that the limit of this function, as x approaches -2 from the right, must be -3. So, as I'm approaching -2 with inputs from the right, I must be getting closer and closer to -3. So I'm going to add a piece of the graph that gets closer and closer to -3. I will make sure that I use an open dot at the left side of that piece of graph, because if that dot was filled in, then the input of -2 would have two outputs associated to it, 4 and -3. That would mean that this wouldn't be a function anymore. Remember, each input can be associated to at most one output. You cannot have two outputs for one input. If you did, this wouldn't be a function anymore. That is why this dot is open. It is not filled in. Then, the value of the function at 3 cannot exist. So I know that at x equal to 3, the function will have no value. I also know that as I'm approaching 3 from the left, the value of the function must be -2. As I'm approaching 3 from the left, the value of the function must be getting closer and closer to -2. So I'm going to draw a piece of the graph that gets closer and closer to -2. Note that I have to end this piece of the graph with an open dot because the value of the function at 3 cannot exist. Then, the limit from the right of this function as x approaches 3 from the right must be 2. I find 3, I approach it from the right, and I know that the value of the function must be getting closer and closer to 2. So I must be getting closer and closer to this point. So I will draw a piece of the graph that gets closer and closer there, again making sure that the function is not defined at x equal to 3. We can improve this graph. For now, this function doesn't show what the value of this function is at x equal to 1, for example, or at x equal to 1/2, or at x equal to 0. To fix that, I can connect some pieces of this graph. For example, I can connect the two bottom pieces. Now, the function is defined for all inputs besides the input of x equal to 3. We know that the function was not supposed to be defined at x equal to 3. I want to point out that you could not connect the bottom piece with the top right piece. If you did so, this wouldn't be a function anymore. The input of 2 would be associated with this output and with this output. So one input would have two outputs. this would not be a function anymore. Similarly, you couldn't connect the first piece with the third piece. If you did, then again, the input, there would be inputs, in this case the input -1, that would have two outputs associated to it. This would not be a function. So the only way you can improve this graph is to connect the two bottom pieces. Now, this is a function that satisfies all the conditions on the right side and is defined for all x's besides x equal to